Welcome! Today, we'll dive into solving LeetCode problem number 2051, titled The Exact Official Title of LeetCode Problem 2051. We'll explore different approaches to this problem while considering their efficiency and trade-offs. Let's get started. In this problem, titled The Exact Official Title of LeetCode Problem 2051, your goal is to determine, insert actual problem details here. Let's start by understanding the input and output formats. The input will be, insert detailed input format and type specifications here, which outlines the exact structure and types of data you can expect to work with. The output, on the other hand, will be, insert detailed output format and type specifications here, which defines the format and type of data your solution should produce. To make this clearer, let's look at some examples. In example 1, the input is, insert input example here, and the corresponding output is, insert output example here. This illustrates how your solution will process the input to produce the expected result. Here's an explanation for example 1, insert detailed explanation for this example here. This breakdown helps us understand the logic and steps involved in solving the problem for that specific scenario. Now, consider example 2. The input is, insert input example here, and the output is, insert output example here. Again, this demonstrates how the problem's requirements are met through the solution. For example 3, which is an edge case, the input is, insert edge case input here. These examples are designed to help you identify patterns and edge cases that are crucial for developing a robust solution. For example 3, the output is, insert edge case output here, and here's the explanation, insert edge case explanation here. This edge case highlights a unique scenario that your solution must handle correctly, ensuring it adheres to the problem's constraints. Speaking of constraints, these are detailed as follows. Insert detailed constraints here. These constraints set the boundaries within which your solution must operate efficiently. Additionally, examples of edge cases that fall within these constraints are examples of edge cases that fall within these constraints. When working on this problem, it's important to ensure your solution not only handles standard cases but also performs well for these edge cases. Finally, the problem requires, insert high-level intuitions or complexity considerations, so be mindful of optimizing for both time and space complexity. By considering all these factors, you'll be able to craft a well-rounded solution. To tackle this problem, we began by exploring several approaches to ensure we could identify the most efficient solution. One of the first methods considered was the brute force approach. The intuition here is quite straightforward. We systematically evaluate all possible configurations or combinations in the problem space. For instance, if the problem involves evaluating every pair, subset, or arrangement, we would use nested loops to iterate through all possibilities. While this method is easy to implement and serves as a great way to validate the correctness of our solution, it comes with a significant trade-off. Due to its high time complexity, often n squared, or worse, it becomes impractical for larger inputs. This inefficiency highlights the need for more advanced strategies as the input size grows. Now, to improve upon the brute force approach, we can consider optimized methods, such as greedy algorithms or divide and conquer strategies. The key intuition behind these approaches lies in recognizing patterns or leveraging specific properties of the problem. For example, in a greedy approach, we make locally optimal choices at each step, which can lead to a globally optimal solution. Alternatively, divide and conquer involves breaking the problem into smaller subproblems, solving them independently, and combining their results. These implementations significantly reduce the number of operations, often improving the time complexity to n log n, or even n. However, these methods require careful design to ensure correctness, particularly in edge cases, as improper handling could lead to errors in the solution. Additionally, we can explore alternative approaches like dynamic programming or hashing, which are particularly effective for certain types of problems. Dynamic programming is ideal when the problem involves overlapping subproblems or repeated computations. By storing intermediate results, we avoid redundant calculations and achieve significant performance gains. Hashing, on the other hand, is useful for problems requiring quick lookups, such as tracking frequency counts or identifying pairs with specific properties. Both of these approaches rely on auxiliary data structures to improve efficiency. While they are powerful tools, they do come with trade-offs, such as increased space complexity due to the need for additional storage. These methods require thoughtful implementation, but they can drastically enhance performance by reducing computational overhead. After evaluating these strategies, we selected the optimized approach, specifically leveraging insert-specific strategy here, e.g., a hashing technique for constant time lookups, as the most suitable solution for this problem. A key observation was that, insert problem-specific observation, e.g., the problem's constraints allow us to achieve linear time complexity with the right preprocessing. Additionally, insert AHA moment, e.g., it became clear that sorting the input data would simplify the solution dramatically. This approach was chosen because it strikes a balance between efficiency and clarity, achieving a time complexity of insert time complexity, e.g., n log n, while also scaling well for larger inputs and handling edge cases effectively. While it does slightly increase space complexity compared to brute force methods, the trade-off is well worth it, as it ensures the solution is both robust and performant. Ultimately, this strategy capitalizes on the problem's inherent structure to deliver an optimal and scalable solution. To solve LeetCode problem 2051, the first step is to understand the problem requirements and what the solution demands. This involves carefully analyzing the input and output specifications. For instance, if the input is an array like nums of size n and a target value k, you should clarify the constraints, such as the size limits for n or potential values k might take. The output also needs to be clearly defined, whether it's a boolean, an integer, or another data structure, so there's no ambiguity in what the solution aims to return. Next, pre-processing the input is crucial. If the data is unsorted, you need to decide whether sorting is necessary and weigh its computational cost. Additionally, filtering out irrelevant data, such as duplicates or invalid values, can reduce the problem size, making the solution more efficient and easier to manage. Choosing the right data structure is pivotal for designing an optimal algorithm. For example, a hash map is perfect for scenarios requiring frequent lookups, as it provides an average time complexity of 1. When working with problems that involve finding maximum or minimum elements, a heap can be highly effective. Depending on the task, you might use a min heap or max heap to streamline operations. For problems involving subarray or substring constraints, the sliding window technique is a game changer, often reducing the time complexity from n squared to n. Beyond data structures, the choice between iterative and recursive approaches depends on the problem's nature. Recursion shines in divide-and-conquer strategies like merge sort, while iteration might be preferable for dynamic programming or traversal tasks. Lastly, handling edge cases thoroughly is essential to ensure the solution's robustness. This includes testing scenarios like empty inputs, the smallest valid input size, very large inputs, and inputs that might challenge constraints, such as including duplicates or negative values. Optimizing your solution is the next step after designing the initial approach. Start by analyzing the time and space complexity to identify potential bottlenecks. Mathematical insights or techniques like caching through memoization can often help reduce redundant computations. Efficient data structures also play a significant role in optimization. For example, breaking down the problem into smaller subproblems can reveal patterns that enable more efficient solutions. Recognizing overlapping subproblems is especially important for applying dynamic programming effectively. Sorting the input is another common step that can simplify the logic, but it's vital to consider whether the n log n cost of sorting is justified by the benefits. In terms of specific data structures, a hash map is particularly useful for tasks like frequency counting or quick lookups, while heaps are ideal for priority-based problems. Two-pointers are great for managing pairs or subarrays, and stacks or queues are indispensable for problems involving depth-first or breadth-first search. For a concrete example, consider an input where nums equals 1, 2, 3, 4, 5, and k equals 3. To solve this, you can use a sliding window approach. First, initialize a window of size k and calculate the sum of its elements. Then, slide the window one step at a time across the array. With each step, update the sum by adding the next element in the window and subtracting the first element from the previous window. Throughout this process, track the maximum sum encountered so far. This method ensures you only make a single pass across the array, yielding a time complexity of n. The space complexity remains 1, because no additional data structures are required beyond a few variables to keep track of the current sum and the maximum sum. Handling edge cases is an essential part of crafting a reliable solution. For example, if k is greater than the length of the array, it's important to return 0 or handle this as invalid input. If the array contains all negative numbers, ensure the algorithm doesn't fail and returns the correct result, such as the least negative sum for a subarray of size k. If the array is empty, return 0 to avoid errors. To further optimize the solution, you can pre-compute prefix sums to eliminate redundant calculations during the sliding window process. Another powerful optimization involves using a deque to maintain indices for maximum or minimum calculations, which is especially useful in sliding window problems. These optimizations can significantly enhance the efficiency of your algorithm and ensure it performs well across all edge cases. The provided solution calculates the minimum average difference for a given list of integers. Let's break it down step by step. 1. Initialization. The variables total_sum and left_sum are initialized. Total_sum holds the sum of all elements in the list, and left_sum will track the cumulative sum of elements as we iterate. Min_average_diff is set to infinity to store the smallest average difference encountered, and result_index is initialized to -1 to store the index corresponding to the minimum average difference. 2. Iterating through the list. A loop iterates through each index I of the input list nums. At each step, left_sum is updated by adding the current element. The left average is calculated as left_sum divided by the number of elements included so far, I plus 1. The right sum is calculated as the remaining total sum minus left_sum. The right average is then computed. If the current index is the last element, the right average is set to 0 since there are no remaining elements. The absolute difference between the left and right averages is calculated. 3. Tracking the minimum average difference. If the computed average difference is smaller than the current min_average_diff, the minimum is updated, and the corresponding index is stored in result_index. 4. Returning the result. After the loop completes, the index corresponding to the minimum average difference is returned. The algorithm is efficient, with a time complexity of O(n), due to the single loop and constant time operations within the loop. It handles edge cases such as single-element lists or lists with uniform values seamlessly due to its design. This ensures correctness and optimal performance for all valid inputs. In this implementation, we first import the necessary Java utilities and define the solution class. The core method, minimum average difference, takes an integer array nums as input. The goal of this method is to find the index where the absolute difference between the average of the left and right subarrays is minimized. We start by calculating the total sum of all elements in the array using a loop. This total sum will help in computing the right subarray sums efficiently later on. Next, we initialize several variables: left_sum to keep track of the cumulative sum of the left subarray, min_average_diff to store the smallest average difference we encounter, and result_index to store the index corresponding to that minimum difference. Now, we loop through each element in the array. For the current index I, we update the left_sum by adding the current element. Using this left_sum, we calculate the average of the left subarray as left average. Similarly, the right sum is computed as the difference between the total sum and the left sum. If the current index isn't the last one, we calculate the average of the right subarray as right average, otherwise, we set it to 0 since there are no elements on the right. The absolute difference between the left and right averages is then calculated as average diff. If this difference is smaller than the min-average diff we've encountered so far, we update min-average diff and store the current index as result index. Finally, after completing the loop, we return the value of result index. This index corresponds to the position in the array where the absolute difference between the averages of the left and right subarrays is minimized. The use of variables like left_sum and right_sum ensures that our implementation is efficient, and the logic handles edge cases, such as when the right subarray becomes empty. This concise yet robust approach ensures that the solution works for arrays of varying sizes and values. In this problem, we are tasked with finding the index in the array nums where the absolute difference between the average of the left and right subarrays is minimized. To clarify, for any index I, the left subarray consists of elements from the start of the array up to I, and the right subarray consists of elements after I. If there are multiple indices with the same minimum average difference, we are required to return the smallest index. For example, when nums equals 2, 5, 3, 9, 5, 3, we initialize some variables to help us solve the problem. N, which is the length of the array, is 6, total_sum, representing the sum of all elements in nums, is 27, left_sum, which will track the cumulative sum of the left subarray, starts at 0, min_average_diff, which keeps track of the smallest average difference, starts at infinity, and result_index, which stores the index with the minimum average difference, starts at -1. These initial values set the foundation for iterating through the array to calculate the required averages and differences step by step. Now, we begin the iterative process to compute the average differences for each index. For I equals 0, we add the first element, nums, 0, equals 2, to left_sum, making it 2. The left average, is calculated as left_sum divided by the number of elements in the left subarray, which is 2/1 equals 2. The right sum, right_sum, is the total sum minus left_sum, resulting in 27, 2 equals 25. The right average, right_average, is right_sum divided by the number of elements in the right subarray, which is 25/5 equals 5. The absolute difference, average_diff, is the absolute value of left_average right_average, giving abs, 2 to 5, equals 3. Since this is smaller than min_average_diff, we update min_average_diff to 3 and set result_index to 0. Next, for I equals 1, we add nums, 1, equals 5 to left_sum, making it 7. The left average becomes 7/2 equals 3. And the right sum is 27, 7 equals 20, with a right average of 20/4 equals 5. The average difference is abs, 3 to 5, equals 2, which is smaller than the current min_average_diff, so we update min_average_diff to 2 and result_index to 1. For I equals 2, we add nums, 2, equals 3 to left_sum, resulting in 10. The left average is calculated as 10/3 equals 3. The right sum becomes 27, 10 equals 17, and the right average is 17/3 equals 5. The average difference remains abs, 3 to 5, equals 2, which is equal to the current min_average_diff, so no updates are made to min_average_diff or result_index. Moving to I equals 3, we add nums, 3, equals 9 to left_sum, giving 19. The left average now becomes 19/4 equals 4, and the right sum is 27, 19 equals 8, with a right average of 8/4 equals 4. The average difference here is abs, 4 to 4, equals 0. Since this is smaller than the current min_average_diff, we update min_average_diff to 0 and set result_index to 3. This marks a new minimum found at this index. For I equals 4, we add nums, 4, equals 5 to left_sum, resulting in 24. The left average becomes 24/5 equals 4. The right sum, now 27 to 24, is 3, and the right average is 3/4 equals 3. The average difference is abs, 4 to 3, equals 1, which is larger than the current min_average_diff, so no updates are made to min_average_diff or result_index. Finally, for I equals 5, we add nums, 5, equals 3 to left_sum, giving 27. The left average is 27/4 equals 4, while the right sum becomes 27, 27 equals 0. Since there are no elements on the right average is 0. The average difference is abs, 4 to 0, equals 4, which is larger than the current min_average_diff. As a result, min_average_diff remains 0, and result_index stays at 3. Thus, the final result for this example is result_index equals 3. In the second example, where nums equals 1, 1, 1, 1, 1, we initialize the variables, n is 5, total_sum is 5, left_sum starts at 0, min_average_diff is set to infinity, and result_index is -1. For I equals 0, adding nums, 0, equals 1 to left_sum gives 1. The left average, left_average, is 1/1 equals 1. The right sum becomes 5, 1 equals 4, and the right average is 4/4 equals 1. The average difference, average underscore diff, is abs, 1 to 1, equals 0. Since this is smaller than min underscore average underscore diff, we update min underscore average underscore diff to 0 and set result underscore index to 0. For I equals 1, adding nums, 1 equals 1 to left underscore sum gives 2, with a left average of 2 / 2 equals 1. The right sum becomes 5, 2 equals 3, and the right average is 3 / 3 equals 1. The average difference remains abs, 1 to 1 equals 0, and no updates are made as the current min underscore average underscore diff is already 0. For I equals 2, adding nums, 2 equals 1 to left underscore sum results in 3. The left average is 3 / 3 equals 1. The right sum is 5, 3 equals 2, and the right average is 2 / 2 equals 1. The average difference, abs, 1 to 1 equals 0, is still equal to the current min underscore average underscore diff, so no changes are made. For I equals 3, adding nums, 3 equals 1 gives left underscore sum equals 4, with a left average of 4 / 4 equals 1. The right sum becomes 5, 4 equals 1, and the right average is 1 / 1 equals 1. The average difference remains abs, 1 to 1 equals 0, so again, no updates are necessary. Finally, for I equals 4, adding nums, 4 equals 1 results in left underscore sum equals 5, with a left average of 5 / 5 equals 1. The right sum becomes 5, 5 equals 0, and since there are no elements on the right average is 0. The average difference is abs, 1 to 0 equals 1, which is larger than the current min underscore average underscore diff. Thus, min underscore average underscore diff remains 0, and result underscore index stays 0, making the final result here result underscore index equals 0. In the final example, where nums equals 10, the array contains only one element. We initialize the variables, n is 1, total underscore sum is 10, left underscore sum starts at 0, min underscore average underscore diff is set to infinity, and result underscore index is -1. For the only index, I equals 0, we add nums, 0 equals 10 to left underscore sum, resulting in 10. The left average, left underscore average, is 10 / 1 equals 10. The right sum, calculated as total underscore sum left underscore sum, is 10 to 10 equals 0, and since there are no elements on the right average is 0. The average difference, average underscore diff, is abs, 10 to 0 equals 10. Since this is smaller than min underscore average underscore diff, we update min underscore average underscore diff to 10 and set result underscore index to 0. As there is only one element in the array, the final result is result underscore index equals 0. In this problem, we are tasked with calculating the average differences efficiently, and to do so, we must analyze how the function processes the input. First, we have the pre-computation step where we calculate the total sum of the array nums using the sum function. This step iterates through the entire array once, making its time complexity O, n, where n is the length of nums. Next, we have the main loop that iterates over each element of nums. Within each iteration, we perform a series of constant time operations, updating the left underscore sum, calculating the left and right averages, and determining the absolute difference. Each of these computations is O(1). Since the loop runs n times, the total contribution of the loop is O(n). When we combine the O(n) time for pre-computation and the O(n) time for the loop, the overall time complexity of the function is O(n). This demonstrates that the solution is efficient and scales linearly with the size of the input. Now, let's turn our attention to the space complexity of the function. The first factor to consider is the input array nums, which is passed as an argument. The memory required to store this input is O(n), as it depends on the size of the array. Beyond the input, the function uses a few additional variables to perform its computations, such as n, total underscore sum, left underscore sum, min underscore average underscore diff, and result underscore index. These variables each take up a constant amount of memory, contributing O(1) to the space complexity. Importantly, the function does not create any extra data structures or use recursion, which means there are no additional memory overheads. Therefore, the total space complexity is determined by the input storage, resulting in O(n). This ensures that the function is efficient in terms of memory usage and does not require more space than is necessary. To appreciate the efficiency of this solution, let's compare it with a brute force approach. A naive solution would involve recalculating the left and right sums for every index I during the loop. Specifically, for each index, the left sum would require summing the first I plus 1 elements, while the right sum would involve summing the remaining n(i1) elements. This leads to a nested summation structure, with the time complexity becoming O, n squared. In contrast, the given solution optimizes this process by maintaining a running sum for the left side and using the pre-computed total underscore sum to compute the right sum. This eliminates redundant computations and reduces the time complexity to O, n. Additionally, the function maintains its O, n, time complexity across all scenarios, whether we consider the best, average, or worst case. Since the loop executes exactly n iterations regardless of input size or content, the function's performance remains consistent and robust even for large arrays. To mathematically validate the time complexity of the function, we can define t, n, as the total time taken to process an input of size n. The pre-computation step, which calculates the total underscore sum, is an O, n, operation. The loop, which involves n iterations with constant work in each iteration, contributes O, 1, asterisk n, which simplifies to O, n. When we combine these two contributions, t, n, equals O, n, plus O, n, equals O, n. This confirms that the overall time complexity is linear. For space complexity, we consider both the auxiliary variables and the input storage. The auxiliary variables, such as n, total underscore sum, and others, require O1 space, as their memory usage does not grow with the input size. However, the input array nums contributes O, n, to the space complexity, as it depends on the size of the input. Therefore, the overall space complexity is O, n, which is optimal given the problem constraints. When solving problems, there are a few common mistakes that can trip you up. First, not handling edge cases in the input is a frequent issue. For example, if you don't explicitly test scenarios like empty inputs, single element arrays, or inputs where all elements are the same, your solution might either produce incorrect results or fail entirely. Always take time to consider and test these edge cases. Another pitfall is the inefficient use of data structures. If you rely on nested loops or redundant structures, you could accidentally increase the time complexity of your solution, turning something that could run in O, n, into O, n squared. Choosing the right tool, such as a hash map, set, or heap, is critical to achieving efficiency. Additionally, overlooking problem constraints like input size or value ranges can lead to solutions that perform well on small test cases but time out or exceed memory limits on larger inputs. Finally, if duplicates are relevant to the problem, forgetting to account for them can create errors, especially in scenarios involving sorting or operations that rely on uniqueness. Ensuring proper handling of duplicates is key to getting correct results. Another common mistake is misusing libraries or built-in functions. For instance, in Python, using sort instead of sorted might unintentionally modify the original list, which can lead to bugs and confusion. Clarity and correctness are especially important in an interview setting, so make sure you fully understand how these functions behave. Now, when preparing for interviews, focus on recognizing patterns in the problem structure. Many problems, especially those involving arrays or strings, can be approached using techniques like sliding windows, two-pointers, or hash maps. It's also important to weigh trade-offs between time and space complexity. For example, while using a hash map may require additional memory, it often allows you to reduce the time complexity significantly. Always be ready to explain why you chose a particular approach. Asking clarifying questions is another critical skill. Problem statements are often intentionally vague, so be proactive in confirming the constraints, input sizes, and expected outputs. Lastly, remember that starting with a brute force solution isn't wrong, it helps you establish correctness. Once you've done that, you can refine your approach into something more optimal. Interviewers value a clear and logical thought process over rushing to the final answer. Practicing related problems can strengthen your understanding of key concepts. For instance, LeetCode 217 contains duplicate is a great way to practice using hash sets for quick lookups. LeetCode 49, group anagrams, is another excellent example that builds on string hashing and grouping techniques. Problems like LeetCode 1, 2 sum are foundational for mastering hash maps and two-pointer strategies. Similarly, LeetCode 3, longest substring without repeating characters, focuses on optimizing sliding window techniques. Beyond specific problems, it's also helpful to explore alternative approaches. Sorting is a great choice when you need order-independent comparisons, though it typically runs in O, n log n. On the other hand, hashing can often achieve linear time solutions, though it requires extra space. Brute force, while inefficient, can be a useful starting point to fully understand a problem. From there, you can introduce optimizations like dynamic programming or greedy algorithms to improve performance. Certain techniques are especially powerful for improving efficiency. Sliding window and two-pointer methods are particularly effective for problems involving contiguous subarrays or substrings. These approaches can reduce time complexity from O, n squared to O, n, making them indispensable for handling larger inputs. Another valuable strategy involves heap-based solutions. If you're tasked with finding the top k elements or solving similar problems, heaps or priority queues are an excellent choice. They allow you to achieve O, n log k, time complexity, which is often the most efficient way to approach these scenarios. Mastering these techniques will give you a significant advantage when tackling a wide range of problems. Great job! In summary, we tackled LeetCode problem number 2051 with an efficient solution. Remember to focus on both understanding the problem and optimizing your approach. Thanks for joining me today, and don't forget to check out other problems to keep improving. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!